All right, folks. Hope you're all turning in. This is our last topic, angular momentum. And, if we consider the fact that we've talked about angular motion, then we talked about angular energy, then torque, which is how you get to move something or make it rotate, it would make sense that we'd have a full parallel of items that we've talked about across the year, and momentum was the last thing we kind of talked about for translational motion. So here it is, the last thing we're talking about for angular motion. And a good way to kind of look at these things is to consider all the parallels we've seen so far. So what I mean by that is consider going back to the very beginning of this. We had motion equation, something like V equals AT plus V naught. All right? Well, no, in this class it's V final equals AT plus V initial. So with angular motion, we had omega final equals alpha T plus omega initial. And I know you understand that I don't have to go through all of them. We had some kind of relationship here between angular and linear, so we could say things like V equals omega R if those things are synced up together. This is still motion equations. And I could write this out for each of the different motion equations. I'm not going to, because we also know that there's also something like energy. So for translational, we had 1/2 mv squared. And for rotational, we had 1/2 I omega squared. Clearly very similar. The portion here that's about inertia is m, and the portion here that's about inertia is I. We understand that I is more complicated when you're rotating, but that they still serve the same purpose. They represent the inertia of the system, and it tells us how much it resists changes in motion. Then there was, the concept of force is a little bit different, because we would say something like net force equals ma, and for rotational, it's net torque equals I alpha. Again, the inertia plays that big role here. The difference here is that calculating an individual torque took more. We had more things that were necessary to calculate an individual torque than we had for just calculating a force. In most cases, forces were pretty straightforward to calculate, while torques were a little more complicated. And of course, we also had the idea that moment of inertia is more complicated. So you have moment of inertia by shapes. You have things like the parallel axis theorem. All of these things kind of made the rotational portion have kind of more things to do and more things to keep track of. So angular momentum is going to be the final piece of that. And if you remember linear momentum, we had specific things about linear momentum that were important. First, for linear momentum, we had to understand that momentum, lowercase p, was a vector, and it was the product of mass and velocity, and it took its direction from the velocity. We talked about how you change something's momentum, and in that case, it was usually based on a force, and in fact, we had this thing called impulse, and we said there was two parts of impulse. There's the cause, which is force times time, and there's the result, which was the change in momentum. In both cases, it was important for us to realize that the direction of an impulse is the direction of the force, not necessarily the direction of individual momenta. And then we talked about collisions. And with collisions, we had this idea that if there's no external force, the momentum before a collision was equal to the momentum after a collision. So we would say things like m1 v1 plus m2 v2 would be equal to, say, if they stuck together, m1 plus m2 times v. And these are things we talked about with linear momentum. Angular momentum is going to have some similarities, but there are some stark differences. And the first I want to point out is angular momentum has a parallel to linear momentum that I think is fully expected. If we kind of look at all the parallels we had over here, then you can probably predict that angular momentum is going to be something about inertia times something about velocity. And that is it. That is angular momentum. We use a capital L for angular momentum because I guess we're just running out of letters, and it is a vector quantity too. So, like linear momentum, angular momentum is a measure of an object's resistance to changes in motion while moving. So, we talked about an object having momentum as being another way of measuring inertia while moving. So, angular momentum is rotational inertia while moving. One of the things that sets angular momentum apart, that makes it different than linear momentum, aside from the obvious that it's about something rotating, is that generally all of our examples about linear momentum, the object itself, its inertia, never really changed while we watched an object move. It might break into pieces, and we'd watch the individual pieces, or it might stick to another object, and we'd watch those two objects stick together and move together. But generally, the individual objects themselves, their inertia stayed the same. With angular momentum, you can have an object that changes its moment of inertia while it's moving. The ice skater, if we watch them spin, we note that if they spin with their arms, here's my ice skater. I know you guys are definitely looking at my ice skater and saying, wow, that's amazing, and it is. If they're spinning, if they bring their arms in so that maybe you have one up and one down, we know that they spin differently as their arms come in. Well, this is because they've taken their arms, which were spreading out more of their mass, and by pulling it in towards their body, they reduced their moment of inertia, and this changed their rotational rate. So angular momentum is very much about how an object behaves when it's spinning. It's about resistance to changes in its motion, and it has some similar features to linear momentum, but has these differences as well. One of the things that we want to focus on when we talk about angular momentum are problems in which our object is not experiencing any kind of external torque. These are the problems we tend to find with angular momentum. And these are similar to collision problems in that in collisions they weren't experiencing an external force, but with angular momentum we can have somewhat unique kind of circumstances. So consider a record player. Not that anybody knows what a record player is, but I know they're making a comeback, so I'm sure some of you know, and you've probably seen them. So I think I can use this as an example. If we have a record player that's spinning, for example, let's say it's I don't know, let's go with 12 centimeters for the radius, and let's say it has a mass of, they're not particularly heavy, we'll say 80 grams. And we'll say it's a disc. When it's spinning at, let's go with a real record. So let's say it's spinning at 33 1/3 RPM. Let's find out what the angular momentum of the record is. Now, in order to calculate angular momentum, everything will need to be converted to kilograms, meters, and radians per second. So let's start that process real quick. If this is a disc, and I think we can all say a record is a disc, it's going to have a moment of inertia of 1/2 mr squared. And in this circumstance, that'll be 1/2 m, which will be 0.08, times r, which is 0.12 quantity squared. There we've calculated the moment of inertia. And we get this ridiculously small number, 0.000576, and that's kilograms meters squared. All right, set that aside for a minute. Our rotational speed, 33 1/3 RPM. You need to convert that into radians per second. So 33 1/3 rotations per minute. If I want to do some conversion here, I'll need some unit multipliers. I want to get rid of the rotations, be left with radians. So that's going to be 2 pi on the top and a 1 on the bottom. For every 1 rotation, 2 pi radians. And then at the same time, we're going to have to convert the minutes. So for every 1 minute, there are 60 seconds. So take a few moments, bang that out on your calculator. So I get a 3.49 radians per second. All right. So bringing all those pieces together, the angular momentum is equal to I times omega. The I is going to be 0.000576 kilograms meters squared times 3.49 radians per second. Now, this isn't a big deal. The units are nothing special. When I multiply all that together, you're going to get 0.002. Now, the radians go away, and the units kilograms meters squared per second. So now would be a good time to talk about units. There are no special designation for the units of angular momentum. But pay attention to this. When we talked about linear momentum, there was no special name for those units either. They were kilograms meters per second, and that's clearly different than the units for angular momentum. So unlike energy, where rotational energy and translational energy have the same units, it's all energy, angular momentum is a different physical quantity than linear momentum and must be treated as such. It is, however, still a vector, and based on the right-hand rule and the fact that I have it spinning this way, my current rotational direction is into the board, or in this case, into your screen. So when we talk about direction, we still have direction for angular momentum. Now, it's hard to really appreciate angular momentum without demonstrations, and you're going to have to wait for those demonstrations when I return to class. And we will. I've got all the stuff I've left out in the front of the room just for the demonstrations. But when an object has angular momentum, it wants to keep its angular momentum vector pointed in the direction that has been established. This is why you spin a frisbee, because you want the frisbee to stay oriented in the direction that you threw it. So by giving it a lot of spin, if you spin it correctly, it will stay oriented, meaning it'll probably stay nice and flat as it travels across from you to your friend. Try and throw a frisbee without spinning it, and you'll come to grips real quick with why that doesn't work. So this is how you calculate angular momentum. It's not a big deal. It's pretty straightforward. This isn't, though, what you're going to be expected to do. As you probably can expect, our problems dealing with angular momentum are going to have other things occur. So let's talk a little bit about conservation of angular momentum, because that's really where it's at. We're going to keep this as our problem, but what we're going to do is we're going to add something. We're going to say a bug happened to be on the record when it was turned on. Therefore, the bug also has angular momentum because it's part of the record system here. And because of that, it too has angular momentum. Its angular momentum is no different to calculate than what we just did here. As it is part of the record, you could add its moment of inertia to the moment of inertia of the disk, or we could find its angular momentum separately and add the two together. We're going to do that since we already have the angular momentum of the disk. The spider is a point mass. So let's say the spider has mass. Let's give him a little bit of mass to make this interesting. We're going to say he's 10 grams. It's a pretty big spider. and we'll say he's perched right at the edge. The spider would be considered a point mass, so his moment of inertia would be mr squared. In this case, 0.01, and r is going to be 0.12 squared. So we'll get 0.000144. I can't fit the units there, but I'll fit them below. Kilograms, meters squared. Has the same speed because he's on the record, so his moment of inertia, we'll say spider, is going to be 0.000144 times 3.49, giving us an angular momentum of 0.0005 kilograms meters squared per second. All right, so we found the angular momentum of the record, the angular momentum of the spider, so we can get the angular momentum of both the record and the spider. And all we gotta do is add these two together because they are spinning in the same direction, they're part of the same system. So 0.0025 kilograms meters squared per second. So here's the thing. The reason I bring this problem up is, let's say that we turn the power off to the record and that there's no friction acting on the record. So the record is free to spin, no external force. What happens if the spider decides to walk towards the center of the record? Nothing about the record changes, except the fact that the spider's moment of inertia is now being reduced. And since the spider is part of the system's moment of inertia is now changing. And since the system's moment of inertia is changing, the angular speed is going to have to change. Now, to explain that, consider that there's no external torque acting in the system. This is momentum. And momentum, as we've discussed, is an object's resistance to changes in motion while moving. So if there's no external torque, then this system's momentum has to stay the same. So this is kind of like what a collision is like for rotational motion. It's another aspect of rotational motion. Consider if I drew it like this. We have the angular momentum of the system times the angular speed. If the angular momentum of the system gets smaller, make a little I here, then the angular speed is going to have to get bigger so that these two things can stay equal. So here's what I'd like you to consider. If the spider walks to the center, basically what happens if the spider makes its value for r 0? How does this affect the speed of the record? We know the speed of the record is 3.49 radians per second, which is actually 33 1/3 revolutions per second. So for us to figure this out, what we're going to do is we're going to figure out what the spider's new angular momentum is. So we'll start by finding his moment of inertia, which is mr squared. His mass is still 0.01 kilograms, but now his radius is like 0 because he's standing on the center. This effectively makes his moment of inertia 0 for the time being. That also means that the spider's angular momentum is going to be 0 times 3.49 radians per second. So his angular momentum is 0. That's the contribution of the angular momentum of the spider. But here's the thing. The angular momentum of the system has to stay 0.0025. Now, the moment of inertia of the record didn't change. All that changed was the moment of inertia of the spider. So If the spider walks to the center, the moment of inertia of the record plus the moment of inertia of the spider times omega has to still equal what it equaled before. The record's moment of inertia is still the same value, 0.000516. But the moment of inertia of the spider is 0. He's just sitting on the center. His mass isn't anywhere away from the center, so he contributes nothing to the moment of inertia. So now, I don't know what the angular speed's going to be, but I know it's going to be different. So let's figure out what the new angular speed will be. So, work that out. Omega equals 4.8 radians per second. Now, it doesn't seem like a big change, but it was 3.49, and now it's 4.8. So, just to kind of make a comparison, it was spinning at 33 1/3 rotations per minute. But now, at 4.8 radians per second, that's 4.8 radians per second times 60 seconds for every 1 minute. And for every 1 rotation, 2 pi radians. I think it's easier to compare things like rotations per minute than it is to compare radians per second. So let's do this comparison. Multiply by my 60 and divide by 2 pi. And I get 46.3 RPM. So this isn't small. This is a significant change. In fact, this is faster than the other kind of records there used to be. There used to be 33 1/3. There used to be 45s. So that spider walking towards the center makes a significant impact to the speed of the record. But if you're really keeping notes and you're writing down what I'm saying, then the important thing here is that the angular momentum of the system didn't change. As the moment of inertia got smaller, the angular speed had to get bigger to compensate. And that's part of how angular momentum works. Let's consider something for you to try. Let's say I have a merry-go-round. And the merry-go-round is 2 meters across and is 150 kilograms. And it's currently being spun so that it makes 2 rotations every second. That's actually pretty fast. I'm afraid that would probably hurt people. So maybe we'll do 1 rotation every 2 seconds. Yeah, that's good. And let's say that while it's rotating like that, there were 3 children arranged on the outer edge of this merry-go-round, and they're going to walk to the center. Now, they can't all go to the center because they can't all stand there. So they go to a distance that is 0.2 meters away from the center. I'd like you to figure out how fast would the merry-go-round be spinning if there's no external torques acting on the merry-go-round when the children make it to the center. Now, if you're truly following along, what you should do is pause right here and try and work it out. If you're having difficulty or you think you're going to have difficulty, then wait for another few seconds. I'm going to write a few things down and then pause it and try and work it out. So for you guys who think you've got it, pause and come back. You guys who think you need a minute, here's what you need. First, remember the angular momentum before is going to equal the angular momentum after. So that means the moment of inertia of the disk plus the moment of inertia of the kids. There's 3 of them. Oops. Well, they just add. So how do I just do this? All the kids are the same. I'll just put 3 times I for the kids times the initial speed, the before speed. this has to equal the moment of inertia of the disk plus 3 times the kids in their new position times omega after. So you'll need to find this and find this. This is when the kids are standing on the edge. This is when the kids are all grouped together in the middle. This is your starting velocity, and this is what I'm asking you to find. Now, none of this will be possible unless you know the mass of the kids. So let's say each kid is 30 kilograms. That's a good kid size. So now would be an excellent chance for you to work this problem out. You should pause the video and then work it out and come back and see what you get. All right, I assumed you paused the video. You probably didn't, but you should have. I'm going to start the problem by realizing that I have the moment of inertia of the disk. That's going to be the same in both. I just was knock that out. 1/2 times 150 times 2 squared. 2 squared is 4, and half of 4 is 2. So this is just 300 kilograms meters squared. A single kid, when they stand on the edge, is a point mass. So that's mr squared. So I'll make that 30 times 2 squared. So that's 120 kilogram meter squared. Now, this is enough information for me to figure out the total moment of inertia. There are 3 kids, 1 disk, so the total moment of inertia will be 300 plus 3 times 120. 3 times 120 is 360, so this is 660 kilograms meters squared. So if I want the angular momentum, which will be I times omega, I just need to put this in terms of radians per second. It's already in rotations per second, so multiply by 2 pi radians for every 1 rotation, and I get 3.14 radians per second. That means I have 660 times 3.14 radians per second, which gives me a total moment of inertia of 2,072 kilograms meter squared per second. This is the this is the angular momentum of the system. So if the kids walk towards the center, the system should spin faster. Our job now is to figure out how much faster. To do that, it is the moment of inertia that is changing. So let's figure out what the new moment of inertia is, the new one. Still going to have 300 for the disk, but now I have 3 times the new kids. The kids are closer to the center, so let's figure out their moment of inertia. The kids they have a mass of 30 still, but now they are 0.2 meters away from the center. And that gives a moment of inertia of 1.2 kilograms meter squared per kid. So that's a substantial change to the moment of inertia. I mean, that's going to be 3.6 or 303.6. Big difference. So now we know this is the angular momentum. Has to stay the same. I have a new moment of inertia. So what is our new angular speed, the final or the after angular speed? Just take that 2072, divide by 303.6, and I get that my new angular speed is 6.8 radians per second, almost doubled. Actually, yeah, just about doubled. More than doubled, I think. Yeah, more than doubled. So that sucker's traveling a lot faster. This would be quite noticeable if you were one of the kids. All right, you have practice. Please take a moment, try out the practice. It's just out of your textbook. I'm having you submit the practice this evening, so I'm only giving you a few tonight and a few tomorrow. So make sure you do the practice and get it submitted before the end of the evening.